All right. Hello, everybody. This is my critical analysis. I decided to do my critical analysis on this paper. It's the silver catalyzed trifluoromethyl alkynylation of unactivated alkenes with hypervalent iodine reagents. It was published by Xingkang Yang and Gavin Chitsu at the University of Hong Kong, published into the Organic Letters Journal on October 11th, 2019. So I know the title is a lot, but I'm going to kind of go through and unpack everything and kind of focus on what they were doing. But generally, the gist of it kind of follows organofluorine chemistry, which is what I do in my research. So the objectives, in a basic sense, what they're trying to do is find a simple development way to find trifluoromethyl alkynylated products. So all that means is, if you look here in red, you have a trifluoro group, and then you also have an alkyne group. So they're basically trying to form both of those groups within the same molecule in a more simple synthesis, so in a one-step synthesis. So generally, they're trying to use difunctionalization of alkenes to generate this molecular complexity. But the idea here is using a silver catalyst to construct an alkyl alkyne carbon-carbon bond and an alkyl CF3 bond simultaneously by breaking that alkene. So again, using this difunctionalized method of doing both of them under one step. So the background here, I'll start off with some of the reagents they use. So they use an ethyl benziodoxolone reagent, or EBX. So the idea here is the EBX reagents are going to provide the coupling of the sp3 to the sp bond over the unactivated alkene. So once your alkene forms into a radical intermediate, what happens is these EBX reagents kind of trap, I guess, that radical and form that sp to sp3 bond. So it's kind of like a coupling reaction, what's going on, but it's going through a radical intermediate instead. Some of the interesting work with these reagents I found was from Studer et al. Here. They used electrophilic nitrogen radicals to react with unactivated alkenes. So in a similar way, it's just instead of CF3, they were finding more nitrogen and oxygen containing. But this is kind of the idea, or at least one of the ideas, similar idea of what's going on with this paper, what they're trying to do. Here's kind of a simplified mechanism just to kind of wrap up what I was saying. So again, formation of this radical just through a radical species, and then this is your EBX reagent, and again, it's just trapping into this intermediate, where now you're breaking that CF3 bond, or sorry, that alkyne, and you are getting this alkene radical, which is a lot happier, reforming that pi system, generating that carbon to, or that sp3 to sp carbon bond, and then you're left with your byproduct here, this radical. That's basically the gist of how they work. Talking about CF3 radicals now. So there has been evidence of them being generated through silver catalysis. So if you can take a TMS CF3 and add a silver species, you can form an AgCF3. So if you look here, that's here. And then what happens is this can actually kick off a CF3 radical with an initiator. So it's pretty rare doing this, and the reason is generally need a lot of external oxidants to regenerate that silver catalyst. But as you'll see in this paper, they kind of noticed that they found a way to reduce the amount of external oxidants to generate, I guess, a more efficient catalyst. But yeah, there's some work by Xing's group, and they used basically this method to form similar CF3 radicals, but they needed 4 equivalents of this oxidizing agent, which can be quite expensive. It's also, if you need 4 equivalents of something just to keep on activating a catalytic cycle, it's not very ideal. And then actually talking about bifunctionalized trifluoromethylation. So there's very little research involving both of trifluoromethylation and another coupling reaction. And all of these generally involve like harsh catalysts or high catalytic loads and whatnot. Also, a lot of these are intramolecular. So, research into intermolecular stuff like this is not as prevalent. But if they can match their objectives, this would actually be the first report of any bifunctional trifluoromethylalkynylation using silver catalysis over an alkene. And then also, as I said before, the silver catalyst can kind of be used in smaller molar amounts, which is actually unexpected, but quite ideal. And you don't need a lot of those oxidizing reagents. So that's kind of where the objectives are coming in and what they're looking into. Yeah. So getting into the relevance. So it's like, okay, why are we so focused on fluorinating molecules, I guess, in a sense? Fluorinated organic chemicals, they're very prevalent in medicinal materials and agrochemicals, some of the other stuff, but those are kind of the big main three. It's estimated that 30 to 40% of agrochemicals and 20% of pharmaceutical compounds are some sort of fluorinated organic molecule. Despite this, organofluorine chemicals are actually very rare in nature. You don't see a lot of organofluorine chemicals. And then whatever is out there, they're usually very big, complex molecules that if you were to take them from nature, you would have to break them down. So a lot of the time with organofluorine chemistry, it relies a lot on synthetic applications. So if you can find new routes to fluorinate organic compounds, it's kind of a hot area of research in a sense. I just kind of to expand on what I was saying, there's a couple fluorinated molecules here. So this is actually Prozac. It's an antidepressant, and you can see it has a CF3 group here, so kind of touching on the pharmaceutical stuff. And here's bromethylene. This is used as a rodent repellent in agrochemicals. So again, just kind of showing you that addition of CF3s onto organic molecules does have impact on some of these industries and stuff, but they rely a lot on synthetics as opposed to natural production. So the relevance involving recycling alkenes. So I threw the word unactivated alkene. Basically what that means is it's kind of context dependent, but it just means you don't have an activating group directly bound to the double bond. So in simpler terms, it's decreased reactivity. So an unactivated alkene would react less than you would think an activated alkene would. But like I said, it's very context dependent on the reaction. But these alkenes, they're abundant chemical feedstocks. A lot of times, especially in petrochemicals. So that means they're pretty cheap. There's a lot of them kicking around. There's a lot of different varieties of them. So being able to make complex molecules from these pretty prevalent alkenes, I think is big for industrial reasons. So I think that's kind of cool. Alkyne coupling. So the relevance behind here, it's like, why do we want to stick? Like, I get that we're fluorinating, but why do you also want an alkyne on? Alkynes have very diverse functionality. They're quite reactive in a sense that if you have an alkyne, there's a lot of different reactions you can do to make it into a molecule that you're looking for. So you can see this figure I attached here. This is only some of the hundreds of reactions you could do, right? You can form carboxylic acids, alkenes. There's a variety of stuff that you can do. So basically, if we're able to not only fluorinate a molecule, but actually install an alkyne, the idea is to functionalize that alkyne, you can make so many different fluorinated molecules in a sense. Also, a lot of the time adding sp3 to sp bonds generally involves palladium or copper catalysts. There's not a whole lot of evidence of using silver catalysis. So potentially using a less harsh catalyst might be good for environmental reasons. So, and then of course, when you're dealing with synthetic chemistry, a lot of the relevance comes down to just the chemical and the actual fundamental research. So bifunctionalized reactions generally produce higher yields. you're kind of throwing two steps into one. And they usually use less resources. So this could improve costs, time, and reduce waste as you're using less chemicals over the two steps. So if you can just get both of these steps done within one reaction, generally that, is more ideal. And then, kind of branching off of that, this could lead to more efficient and greener methods of synthesis, which would benefit the economic and the environmental improvement on society. As I mentioned before, a lot of the time you're using harsh catalysts, not the best for the environment. So maybe finding greener methods to produce these compounds would be pretty cool. And then, of course, just the chemistry field itself, better understanding of the chemical processes. So, let's look into silver catalysis a little more. Let's look at coupling reactions through these radical intermediates, functionalizing these unactivated alkenes just from a chemical standpoint, and producing reactions in literature for the actual scientific community. It's always it's overlooked, but it's still very important. So getting into the methods here. Whoops. So the methods of what they actually decided to use. This is just the overall mechanism. I'll kind of simply break it down in a sense. But generally what you're getting is, we talked about the formation of the CF3 radical, reacts with the unactivated alkene to form this A intermediate, which then reacts with your EBX reagent, which again, as we talked about, kind of traps it and will then kick off your product. And just like that, in just a couple steps, you've difunctionalized your alkene. We talked about this, or at least I mentioned this before. What can happen is this radical can actually help reform the silver catalyst. So that's kind of what I talked about, using less of these highly oxidizing products to regenerate the catalyst. This byproduct, this EBX byproduct, can actually help generate that. So you're taking these side products and giving them functions within the reaction. So I thought that was super cool. Within the paper, they actually mentioned that this was not something they were looking into at first. They just kind of realized it after. But it's super ideal. Like I said, you're using less harsh chemicals, less expensive chemicals. But this is kind of just the general methods of what they're kind of going at here. So they used a lot of different of the unactivated alkenes, most of them bearing mild electron donating groups, which kind of made them unactivated in this sense. Again, it's context dependent. They found that the reactions were done under argon at room temperature for 24 hours. So generally benign conditions. So nothing crazy, you're not heating it or anything. And then of course they touched up on, the different catalyst load, the silver species and the activators to kind of test out what was the most ideal. And then obviously characterization through NMR and mass spec confirmed product formation. Here's just some of the common ones that they used. Like I said, they used a whole lot. I didn't want to throw all of them on here, but here's just some of the unactivated alkenes that they decided to go with for their research. A couple criticisms that I noticed within the methods. All of their EBX reagents, or at least almost all of them, had phenyl groups at the terminal end. I read through the paper, I couldn't really see why they used phenyl groups. Why can't you just throw like a CH3 at the end? They didn't really report stuff like that. So that's kind of one thing I looked at. I also noticed the lack of control experiments that they did. So they didn't really focus on other radicals that weren't CF3. They didn't look at activated alkenes. So for example, something like this, it's like, does it work better with activated? Does it not work at all with activated? We don't know. And then obviously other metal catalysts, especially group 11 catalysts, so gold and copper, would these work better? Would these not work better? So I found that the reactions performed didn't really broaden the applications of the proposed mechanism in a sense. Going into the findings. So here's their little matrix of, as I mentioned before, different conditions that they were trying. The ideal conditions, they had silver trifluoroacetate at 10%. Increasing this as their silver source actually, if you look at 18 here, actually produced a smaller yield. So 10% was kind of the lucky number. And then 0.4 equivalents of BIOME, 4 equivalents of your TMS CF3 as your radical source. 0.2 equivalents of sodium acetate to kind of activate your silver species. And then the solvent they used was DMSO at 0.2 molar. Again, they just found this was the best for not getting any side products as well. And then, as I mentioned before, room temperature, 24 hours. But you can see here, they did run a lot of different conditions and whatnot, but these were just the ideal conditions that they found. Their yields were determined not only through like masses and whatnot, but they also determined a lot of them through fluorine NMR. And they noticed that actually different substituted phenyl groups provide different yields on the alkene. I'll get into that a little bit more as we touch up on it. Here is one of the proton NMRs. They did a really good job of characterizing all their products, which I thought was super cool. But here's the proton NMR. I guess the peaks to kind of look at, you have these diastereotopic protons, which would belong to these here. And then you also have this peak here, which would be the propargylic hydrogen here. So you can see pretty good conversion. There wasn't any of the starting material alkene peaks, and you're clearly seeing formation of new hydrogens on what was the old alkene. So based on this, in general, you can say conversion was met. And then furthermore, fluorine NMR, you have this nice CF3 triplet at -65, which is exactly where you would expect it. And you would expect it as a triplet as it's coupling to the two hydrogens neighboring. So again, just based on the NMR, you can see that product formation was being made. And as I said, they characterize everything super, super well. So I thought that was really important. Further going into the findings, so in total, they actually had 36 different unactivated alkenes that underwent trifluoromethylalkynylation in measurable yields. They did mechanistic studies using proton NMR just to kind of prove that that mechanism was the one that they hypothesized did go through. It also kind of helped validate the role of each of the reagents used. And then all of the products they were extracted and purified by column chromatography to generate these final yields. You can see, as I mentioned before, different substitutions on this phenyl group actually led to a pretty broad yield change, which I thought was pretty interesting, just because, adding groups onto here, is it really activating or deactivating that alkene very much, just because it's so many bonds away? But again, I thought that was just kind of cool. And I think that was some good information that you gain when you use so many different starting materials as they did. They looked into functional group tolerance. So they just thought, like, how many different functional groups can we use within this reaction that won't hinder the production of the actual product? And what they found is almost every single functional group had no difference on the product. So there was no side reactions being made. Even using stuff like epoxides here or sulfonates, right? You're still getting these products being made, albeit in smaller yields. But as far as side reactions and stuff, it wasn't hindering, it wasn't messing up with the catalysis or the radical intermediate and stuff like that. The only one they did have an issue with was the aldehyde group, so aryl aldehydes, and that's because you were getting reactivity with the TMS-CF3. They were still able to isolate the aldehyde product, but you can see here they also got this side product where CF3 would react with the actual aldehyde. But other than that, very functional group tolerant, and a lot of that just comes down to the fact that they were using pretty benign conditions in the methods. Another thing, as I touched up kind of on relevance, is functionalizing that alkyne to form other products. So they actually looked into that, which I thought was super cool. So you can see here, they were taking the products and they were undergoing different alkyne reactions to see if addition of that CF3 would maybe hinder what's going on. So they did some click reactions, which are pretty important in biochemical processes. And you can see you form this trinitro ring intermediate, but the CF3 wasn't affected at all. 90% yield, so everything's working good. They could do hydration reactions using a palladium catalyst to form this alkyl, so just completely reducing the alkyne. And then hydration reactions to form these ketone products as well. And again, 86% yield, 95% yield. And then stereoselective alkene formation was also formed. So you're able to form the Z or the E based on different ruthenium catalysts that they use. And again, high yields here. It's no byproducts are being made. So not only are you able to add that alkyne, but it's just further proving that you can functionalize that alkyne and make a lot of different fluorinated organic molecules, which is kind of the gist of what they were getting at. So the assessment, so as far as the objectives, I just kind of broke down the main ones that they were going for and the main ones that they met. I found out that they were able to use small catalytic amounts of silver to form 2 carbon-carbon bonds. They were able to use TMSCF3 as a CF3 radical source through silver catalysis. They were able to use many different cheap and abundant unactivated alkenes and convert them into synthetic building blocks. Mild reaction conditions were used, which helped out with functional group tolerability. And then further functionality of the products provides a diverse range of synthetic pathways. So as far as their conclusions went, I think they were really well supported through characterization and yield calculations. They did the mechanistic studies, they had their predictions, they proved their predictions. And they had such a different variety of product forms, which I think validates the conclusions. They didn't just make a couple products, they made so many different ones. So I think as far as does this method work to generate what they want, I would say that it does, just based on all the evidence that they compiled. Of course, there is criticism though. Again, just touching up, there's not any experiments comparing silver catalysts to other metals regarding the radical formation. Does this only work with silver? Does it not? More diverse use of alkyne functional group. So as I mentioned before, they only had the phenol on the terminal. So I would have liked to see some other EBX reagents being used. They didn't really touch up on the alternative routes. So I guess they provided a general pathway, but there was no discussion comparing how it was done before. So what's the more traditional way to synthesize these molecules, right? Is this way cheaper and greener, doing it over the 1 step as opposed to maybe the 2 steps? Does the application of silver catalysis actually provide more benefits than costs? Or are we introducing, a transition metal catalyst into something we don't have to? That they never touched up on. So I think in that sense, it kind of hinders a lot of their conclusions and a lot of the potential of the paper. As far as future directions, I think that I would like to see them maybe focus more on generation of this difunctionalization along the same carbon. So maybe a formation of this where you have a CF3 that is propargylic to your alkyne. This is a little bit more dived into actually my research, so it might be a little biased, but I think this would be super cool if you're able to use a similar radical mechanism to form maybe a product such as this. In conclusions, I think the paper provides ample evidence to conclude that the objectives were met. I really do. I think everything they wanted to be made, their main objectives were met. I think it was very well written, a lot of evidence. So while I think it has a strong fundamental impact to chemistry, I think its societal impact is still relatively unknown. As I mentioned, they didn't really talk about alternative ways to get these products, or if this way is a better, greener, cheaper way. They just kind of proposed it as a different way. So in that sense, I think further analysis could really help unlock the potential of this research. If you can look into how these target molecules are generally made, and you can conclude that this way is better, I think if they would have mentioned that in the paper, it would have been a lot more relevant and a lot better. But that's the gist of it. That is my critical analysis of the paper. So I hope you guys enjoyed it. And I look forward to seeing all of your guys' presentations in the future. So thanks, guys.